Good morning. I'm Gregory Falkovich, and I'll teach this course, Information Theory for Natural Scientists. First thing that I want you to know is that it's a graduate course, which means that I treat you not as a student, but as a fellow researchers. And it means that I'll try to tell you less about some knowledge and more about how actually to get this knowledge. And another important part in being in a graduate course and being a graduate student is that the role of questions and answers is somehow flipped. When you are an undergraduate student, you are more focused on answers. You want to give right answers. And for questions, you say, okay, any question is legitimate, you can ask any question. As you grow up and you turn into a scientist or engineer, you understand that questions are very important. Questions are much more important. Different people ask different questions. That's what our creativity is expressed here. On the other hand, when you ask a question and then you try to give an answer, it's not that important whether it's right or wrong. It's usually wrong. You work on it. And it's very important to develop your intuition. And to develop your intuition, you need to give answer immediately. And during all this course, I will be asking you questions over and over. And I want you to give answers immediately, at least for yourself. And then start thinking why I gave this answer. What actually was inside me. Because this is what is your developing your own personality and your own mechanism for thinking. Okay? And particularly intuition. Another thing is that this course is based on this book. Everything in this course is in this book. All the formulas, all the problems, detailed solutions of all problems is in this book. So it really means that during the lectures, you are supposed to be more engaged, to be active, to follow my thinking, to follow your thinking, to argue with me and with each other, and not necessarily to write down all the formulas and all the pictures that are here. They're all in the book. You can find them there. Okay? So this is also important. Now, what is the subject of this course? The subject is uncertainty. This is a course which essentially answers the same question over and over. How much and what can we say or do about something that we do not know? And it naturally comes essentially to giving bounds, to giving restrictions, saying we cannot say more than that, we cannot do more than that, or giving the probabilities to different outcomes. And eventually what you'll see is that it's approximately 150 years of developments of imposing restrictions due to uncertainty and our ignorance, first on our ability to do work, and second on our ability to communicate, and then in our ability to think and to do perception, and then in our ability to compute. And it's all this restriction, namely going from classical thermodynamics to communication theory and information theory, to computation theory, to biology, to perception, to brain research, based on the same mechanism, on the same formalism, on the same set of ideas. And this set of ideas starts from what was historically the first example, and it's our restrictions to do work, or turning heat into work. So let me start telling this story. It starts in 1820s, but the origin is, of course, earlier. It's Industrial Revolution. During the Industrial Revolution, people started to burn things to do work on an industrial scale. And then they noticed that sometimes you get more work and sometimes you get less work. You're naturally interested in get more work after you burn some fuel. And so you start asking how efficient could be your thermal engine. So what is a thermal engine? in a really very distilled form, it has the following scheme. It has a reservoir of body with a temperature 1, and there is a heat Q1 which is taken out of this body. Then there is a heat Q2 which is delivered to another body having a temperature T2. And this is usually your environment. This is your engine and your car, and this is your outside air in which you leak heat. So the difference Q1 minus Q2 equal to work is actually what you obtain. So you pay for it. That's what you pay. You buy some coal or you buy some wood, you burn it, you put it into your steam engine, and then out you get work. So you're naturally interested to make this Q2 as little as possible. It's your loss. It's something which is subtracted from your work. And then people will notice that somehow if you burn, for example, coal, which makes T1 larger, then it is more efficient. You get more work out of it. And then people start asking, is there any fundamental inequality, fundamental restriction which bounds this Q2 and tells us that we cannot make it as little as possible? And let's now design it. So it must be expressed through the quantities which are given, Q1, T1, and T2, right? So there are 3 quantities. And apparently, just dimensionally, Q, which is kilocalories or joules, must be proportional to Q1. They have the same dimensionality. So it's definitely that this be something like this. So now, because degrees must cancel out, then there must be a ratio of these temperatures. So now, at this very phenomenological level of thinking, which is essentially dimensional reasoning, is that we need to only to understand whether it will be T1 over T2 or T2 over T1. So what would be the natural guess? Of course, the lower the temperature, T2, the in principle less heat it can absorb, so you would naturally put it like this. So Sadi Carnot did it in 1820. He argued this inequality in a very wrong way. He assumed, he made wrong assumptions, which at this time people believed to be true. Namely, he believed that heat is a separate conserved quantity. So he did not know the first law of thermodynamics or the law of conservation of energy. But still, being a genius, he gave the right answer. This is the right answer. Then you can also write it in the way which we will be very often work, so that you can put all things related to second body in one side and things related to the first body in the other side, and then Carnot inequality, which is the first example of, as we now recognize as entropic inequality, is expressed in terms of the quantity which is heat divided by temperature. And at 50s, Clausius introduced the term for this quantity, and he called it entropy. It starts N like energy, like ability to do something. Energy is an ability to do work, but it continues not with edge, but with trop. Tropos in Greek, it means pass, or it means a turn of a pass. It's something a turn, so there are many ways, and in essentially what we recognize that we really are counting these ways, and that would give us entropy. So this is, at this point, is a purely operational definition. It just says that if you can measure amount of heat, just divided by temperature, and that's your entropy. There is no any microscopic or or informational theory meaningfully, it would take another 50 years to get to this point. But already, this is the first example, and everything else we will be doing all the way to communication theory and brain research follows from this idea. So this is one of the greatest ideas in the history of science and industry, and you see it's dictated by a very, very practical question. So what now, and because of this, traditionally, the basic phenomenological way to answer this question, how much we can say about something we don't know, it's called thermodynamics. And thermodynamics, by definition, it's a phenomenology, namely, we look at phenomena from outside, and we don't go inside and ask what is actually going on, but we do know what are the fundamental properties of our system. And thermodynamics tries to derive restrictions, inequalities, boundaries like this out of some fundamental properties of the system. And systems could be different. You can treat a system of molecules of a gas, you can treat a system of stock market traders, you can take a system of macromolecules who do some kind of biological function, or you can take a genome and ask what is going on when you do transcription in a genome. There are very different systems, but in all of them you know the nature of the system, but you don't know microscopic situation. What are the position of your things? How many money is for this trader or that trader? What kind of deals they do? You don't know it, but you do know the nature. So you want to use the fundamental properties of the system to impose restriction on its behavior. Give you a little bit more fundamental. What are the fundamental properties of the system from which you try to derive restriction on its behavior?
Number of particles? Or
number of particles,
entities,
it's a quantitative characteristic of a system. I'm asking what is the fundamental property of the system?
The interaction between the particles? Oh, the bodies in the system?
its boundary.
Like if it is gas, then
marked.
collision.
Of the
Temperature.
Those are characteristics of the system. I am asking you a fundamental property. So, for example, you're 21st century people, right? Okay, so we are not in the 19th century. You can do thermodynamics of stock market. You can do thermodynamics of a gas. There is a temperature of the stock market, but it needs to be defined. What is really important that you try to identify first fundamental symmetry, invariance, or conservation law, which for mechanical system usually invariance with respect to time translation means that energy is conserved, invariance with respect to space translation means the momentum is conserved. But on the other hand, when you treat stock market, you may say, okay, money is conserved. Unless government is printing them, of course. But for a given system, I have a conserved quantity. So thermodynamics starts from identifying conserved quantity, and that's why the first law of thermodynamics in its traditional sense was what? Conservation of energy. Good. So now, let's do thermodynamics, and I'll do it in an axiomatic way. Of course, thermodynamics, as any science, is inductive. You do something, you do processes, you look at them, and then you try to get what actually is the law which governs these processes. But axiomatic is different. You postulate the law, and then you do. So what it says, that there are, for a given system, state that are characterized by a quantity which is called energy. Again, it could be the amount of money, or it could be something related to your set of macromolecules, etc. Okay? So it is this quantity which you believe is conserved, which means that you are in a situation where, like here, you can measure this. This is measurable. This is work. This is your piston moving, right? But something which means that if I did some work
and it corresponds to a change of energy, you need to say that there must be such processes which we call adiabatic, in which all the changes in the energy are visible. These visible changes is called work. Okay? That means that for a given system, if it's in a state of A, it can pass a state of B, we can always find adiabatic process. Namely, that we can really characterize all states of our system, but energy ascribed to the state. And then the first law of thermodynamics is formulated like this. It changes the change of energy okay? So you did some work. If it's positive, you diminish your energy, but it could be that you could also that this is not equal to this. This difference, which is unobservable, this is observable. We call heat. So the first law of thermodynamics is essentially a religious statement that we believe in the conservation of energy. If you look at, for example, trading system, and you see that these people paid some money, but these people get some money, but there is a difference between them. You assume bribes, or it went something through cryptocurrency or whatever. That will be your hit in terms of stock market. Okay? Invisible part, hidden part of your energy change. So essentially, this is the first law of thermodynamics. Okay? And then, again, in this axiomatic approach, it's usually done by formulating what is the problem of thermodynamics. It's a little bit like the way mathematicians do. And this is that the problem of thermodynamics is to determine the state of a system if you leave it alone for sufficiently long time, or you remove some constraints, etc. Okay? And how you solve this problem? You solve this problem with the help of a second law of thermodynamics, which is a statement that we inferred inductively from Carnot and Clausius. He said, there exists a function, it's a function of energy. Energy we already introduced. There exists some quantity which is called entropy, which reaches its extremum in the equilibrium state. If you take a system in any state, it can have some entropy. If you wait long enough, it could go only up. And then it stops. Okay? What it means? It means that on the plane of energy and entropy, there are some states which are possible, and then there are some states which are impossible. And the line between them is an equilibrium line. Okay? Now, what we expect from this line? Entropy is a function of energy in equilibrium. Anywhere here, entropy is not a function of energy. For any energy, you can have any entropy up to the equilibrium value. But this would be a line. That would be a definite relation between entropy and energy. What do we expect this function to be? Monotonic? Let's start from monotonic. Monotonic? Monotonic?
I say no.
Monotonic? Who say no? Why?
I think in the Ising model, the entropy of high energy states, where all the parts are excited, is small. There's only one state, all are excited.
Good. I thought about computing it in the second hour, but anybody else think why would the entropy decrease with energy? Is it possible? Incidentally, just jumping a little bit ahead, let me define the quantity. It's a definition. When this would be like this would be negative temperature. Are you okay with it? Anybody else okay with negative temperature?
It's obvious. Yes, in Celsius.
Huh?
In Celsius, yes.
Inside this
At this point, this quantity defined up to a constant, incidentally, because what we measured only differences between different states means our energy is defined up to a constant. Okay, so energy could be whatever, you can take it negative. But the same as entropy. Entropy also divided by but the derivatives, oh yeah, they're very important. Okay, of course you're right. Temperature could be negative, and the moment you understand that temperature is a derivative of energy with respect to entropy, or physicists always prefer beta, which is 1 over temperature, which is dsD. And then, I won't hide it from you. Entropy is a measure of how many possible tropos, states in a system. So some systems are such that you increase energy, and at some point there will be less and less states available. For example, you have two-level systems, or I don't know, spins. Okay, so if your energy is very, very large, it means a lot of spins already look in the same direction as the magnetic field. So there is much less possibility. We'll compute it in the second hour, or maybe on the next lecture. Okay, so it's not monotonic, but what we want from it really, from this curve. Monotonic is a statement about first derivative. And we already, some of us are overeducated, and they already seen the system in which this first derivative change sign. Could we require something from a second derivative?
Directionality.
Second derivative, again, it's a scalar with respect to scalar. It's just, it could be positive or negative. Okay? So what we said is the first derivative could be positive and negative. Is the second derivative must only have a definite sign?
Yes,
Why?
because we want a maximum, we don't want a minimum in this function.
No. Maximum and minimum is the following statement. There is a curve, and all the states are below it. Okay? That's it. Which means that it's maximum. For a given energy, you can reach only this value, not higher. So, I mean, this could be whatever you want. But now, I'm pushing you in the making discussion. Yes?
But it has to be continuous?
It has to be continuous, generally. Generally, of course, not. Anything I say on the first lecture, second and third, and maybe first 5 lectures, would be overcome in the later course. So there will be many things which could be. There are phase transition in which you can jump, etc. But at this point, let's say it's continuous, namely the first derivative exists, the second derivative exists. Now, first derivative, whatever, second derivative, must it be of a definite sign?
I think you want maybe a well-defined values of S and E and not have the same value of entropy for several energy. So you want the derivative to be always positive. The second derivative.
You mean that I don't want this, right?
Yeah.
So I don't want equilibrium to have different values, okay? But can I, let's say, afford Z? Because that would be for a given entropy, 2 different values of energy in equilibrium. So you say that this is probably idiotic. And again, trust your intuition, okay? I'm not proving theorems, right? I'm just showing you how you try to approach. We're not doing a thermodynamics, just inventing it from scratch in a very messy way. This is definitely not okay. First of all, it's where are the allowed states? These states, well, of course, you've probably seen phase transition, where there's a Maxwell construction. I mean, you cannot have it. Because if you go up and then you kill this, but there is also higher value. But can you have this?
Yes.
Namely, that all this is your allowed state, but it's possible to have for a given entropy 2 different values of energy. Because, as you said, if my entropy goes down, and if it went up before, then it went up and then goes down, then there will be 2 values for it, right? This is possible, this is not. But what is important property of this curve, which is really crucial for not only for a physical system, but for stock market and for biological system as well.
Convex.
Huh?
It's convex. Like you can.
Convexity. And here, the magic word convexity, which will be repeated over and over on this course. So maybe, I have here entropy. Let me add here another magic word which just appeared. It will appear almost in every lecture in very different disguises. It must be convex. Convexity means that the second derivative is sign definite. Again, we can sometimes people like switching things, turning positive into negative, and so very often we will have concavity, which I would also call convexity. But in this particular case, it's really convexity. And what is important about it is that all possible states are below it, and states which are on this convex curve are equilibrium. What physical or financial statement is the requirement of convexity?
If you take linear combinations of variable states, you still stay in the variable.
Excellent, very good. It means, let me rephrase it, stability with respect to breaking into inhomogeneous parts. Not visible. Let me show it to you. So you have a system at a given energy, and it's in equilibrium having this entropy. Imagine that you break, that the system is spontaneously broken into two parts. One has E plus delta, and another has E minus delta. Energy is conserved. Just one half took a little bit more energy to itself, or money, or whatever, and another part get less. Okay? Now, this new state, this would have this entropy, this would have this entropy, and the new composite system will have entropy, which is their half sum. Right? So now I have two systems. At this point, I explicitly assume that the entropy is additive for two systems. Means that I'm now neglecting interaction between different parts, but I also assume that the energy is additive for these two systems, which means that I'm also neglecting interaction part. And of course, in the second part of the course, the most interesting parts about entropy, which will be mutual information and other things which are related to interaction. But at this point, we're looking at the main part. So what I'm saying, if my system is so large that breaking into two parts, energy is the sum of these two parts, neglecting energy of interaction, and the entropy is also sum of these parts, that the entropy of a composite state is this one. What convexity guarantees me? That it's not a real maximum. This is a real maximum. The real maximum is a homogeneous state. So convexity of entropy energy curve guarantees stability of a system with respect to breaking into inhomogeneous parts. Okay? Good. So let's finish the first hour and reiterate the last minute what we've actually done. Okay? So, more or less, we've seen that some interesting statement about some inequality, that's what thermodynamics does. It does inequalities, right? Appeared and introduced this quantity. We now start to build an axiomatic formalism for it, which consists of two things. And we establish the most important part of the relation between energy and entropy is that in equilibrium, it's a convex curve. All the states of a system lies below this curve. Okay? 15 minutes break, 10 minutes break, how much you want?
15.
15? Good. See you in 15 minutes.
It was also.
Well, it's a little bit idiotic to talk to people who aren't here, but because they will be watching, there are about half people who will see. Maybe some people are really in, but the record, all the lecture will be recorded, and the records appear after a while, so people can watch. But I hope that you people who are here in the room, you recognize that it's a totally different experience to watch a record and to, real time participate, trying to invent thermodynamics or discover second law. We'll be discovering at least 4 different forms of second law of thermodynamics, so we're just warming up. Okay, good. So now let's look at this curve and realize the following things. That if I'm at a given energy, then I can go up and reach equilibrium as a maximum of entropy at a given energy. But the same point, I of course can reach going from here. I can reach by any trajectory, but particularly revealing is that if I look at this point, it realizes a minimum of energy at a given entropy when temperature is positive. When temperature is negative, so what I've realized equilibrium, which is a maximum of energy at a given entropy. Okay, so in a sense, they're both legitimate. When we derive, it will be apparently in the next lecture, when we derive the two-level system and the negative temperature state of it, then we'll recognize that it's a very, very special type of system. But for example, in biology and in finance, it's a very, very usual state system with a negative temperature. But this kind of a normal state, it's a little bit like a ball. For me, it was a surprise. I was teaching this course at NYU a couple of years ago, and after me, there was lectures of great mathematician Misha Gromov, who gave a course on isoperimetric inequalities. And I'm not a mathematician, but just a pleasure to see great mathematicians. And it was right after me, so in the same room. So I just stayed, and he started giving a course more or less about entropy, and then we talked about it. And when mathematician look at such things, what he sees that a ball realizes a maximum of volume under a given area, or a circle realizes maximum, or it realizes a minimum area under a given volume. And it's unbelievably rich mathematics which comes out of it. That's what you usually hear from mathematicians. You physicists just understand how rich are objects that you occasionally stumble upon. Incidentally, Perelman did his work on Poincare conjecture, also using entropic principles, etc. So this is a very, very rich set of mathematics behind it. I just want you to know if somebody inclined. But what I want to say is that I'm trying on the lectures, namely on Mondays, to give you pictures, hand waving, and all this. On Tuesdays, there will be tutorial. I'm also doing I don't have methodology, I don't have teaching assistant, so I'll be doing tutorials too. I'll give you formulas. Okay, so I'll just now write formulas, which unfortunately we have tomorrow. We don't have tutorial, and week after that we don't have tutorial because of tomorrow Yom HaShoah. I just write a formula and then I'll derive it on tutorial and also teach you how to do Jacobian's formalism and all this stuff. Okay, so I'll try to do lectures as free from formulas as possible. It's impossible, but more or less. But on tutorials, and again, for people who aren't physicists or not less interested, you can skip tutorials. Well, you will need to solve the problems, but it's somehow in between. So the formula which stands here is that, of course, what I have entropy, which is a function of energy, but also generally for mechanical system, it can be function of V and magnetic moment electric charge, there are many other things which I would call x. So when you move here, right, so your energy stays, but these other variables change, okay? So in a sense, when you're looking at the extremum, so I'll write formula, which is some of you may remember from partial derivatives. So if I'm interested in the, let's say, dE dx under control x, and I want to relate it to ds dx under the constant e. So now I'm talking about this direction or that direction, right? That was quite intuitive without any formulas, but I just want to write you a formula which you. So do you know how they are related? What is also a factor here? Must be times, ds dx, x is already here, so it must be e somehow in the denominator, right? And s in the denominator, right? Because it's extra s. So what it stands here is ds under x, and believe it or not, the sign minus. You learned it probably when you were undergrads, but this formula is so ugly that you immediately forget it every time you see it. But I'll teach you in tutorials a very beautiful formalism called Jacobians, in which such formula, which is easily flying off the shelf. Yes?
Are these variables x, they're not necessarily conserved like the energy, right?
Absolutely not. It's volume, number of particles. Well, some of them are. For example, charge is conserved. Namely, it's additive. So you have two systems, you add charges to it. Okay? But this is just a formal exercise saying that I have a function s which depends on e and on x. So I can differentiate it with respect to e under the constant x, and I differentiate it with respect to x under the constant e. There is a formalism which I don't want to spend time on the lecture, but I'll do it on tutorials because, at least for physicists, it's really something that it's very handy. And it's a very, very beautiful formalism, which I also learned pretty late, and I was just struggling. One of the reasons that people struggle with thermodynamics is all these idiotic partial derivatives. And the moment you learn your Jacobians, are just very easy. So what I just want to tell you is that behind any picture there is a formula, right? So what it tells you that when this guy turns into zero, right? Namely, you are in the equilibrium, right? And this is, of course, inverse temperature, right? It's just by definition. Where is my temperature? Yeah, here is my temperature. All right? So it tells you that when your temperature is positive, this guy, then this thing is turned into zero together with this, and if you differentiate it one times more, I need to show you some formulas, otherwise you would think that I'm just hand-waving my way. Here, you don't differentiate this at equilibrium because it's already zero, right? So what you do, you differentiate this one with respect to x, and it gives you under E against times temperature. So what it tells you exactly is that if your temperature positive, then positive derivative here, namely maximum, corresponds to the minimum here, and positive second derivative means minimum, positive second derivative, right? Then it corresponds to maximum over there. So apart from kind of this simple picture, you can write respective formulas. Okay, and on tutorials we'll do all this machinery. I just now want you to know that it exists. Yeah.
E is the energy injected to the system, right? It's not.
E is the energy of the system.
But if it's energy of the system, then there's the same information comes through like the identity of the particles participating.
Yeah. If you define this function E as S as a function of this, it contains the same information as E as S of X. Exactly.
No, I mean X. The information contained in X. If E is the entire energy of the system, then part of its information is also contained in X.
Yes, I mean X is, let's say, charge.
Okay.
So you add extra charge, you change energy. That exactly means that your energy is the function of your x.
So why in the display? So this I'm okay with. This the set of S being a function of both energy and x. That's where I have more of an
What
issue.
your problem of this or of that?
The left one.
This one.
Yeah. Because
The same entropy. I mean, you have the energy, so you can add some charge, but you can decrease. You can add some magnetic moment, but you can decrease some electric charge, and energy stays the same.
yeah, so E is
But
partially
entropy changes.
but E is partially dependent on the variables in x.
No, it depends. That's what makes
That's
this.
what bothers me.
That's what makes this thermodynamics is particularly difficult. Is you always need to remember what you want to keep constant, right? So of course, if you mentally say, well, energy depends on everything. Well, it depends. This means your moment you say energy depends on everything, you consider this function. When you consider this function, energy is a variable. It's not a function. Okay? You say, I have this energy in the system. Now, what is the entropy? Well, it depends how you get this energy. You can get this amount of energy from electric energy or from magnetic. The same amount of energy, you can have more magnetic, less electric. Entropy will be different. Energy is the same.
Yeah.
So now your energy is your variable and your entropy is your function. Okay?
And we're okay with that. I mean, the functions are okay.
So be my guest. I mean, use what I mean. The beauty of thermodynamics is it's just functions. It's called thermodynamic potentials. So this function contains the same information as this function, and these formulas are just expressed one through another. Okay.
And it all works because it's in equilibrium. If it
Yeah.
weren't in equilibrium,
So
then
it's just a physicist way of thinking that energy is determined by everything. Yeah, but on the other hand, you can say at a given energy, 5 kilojoules in the system, I can have different parts of it. I can have more kinetic and less potential, or less kinetic and more potential. Entropy will be different. Energy is the same. Okay. More questions here.
Yes, I'm sorry,
Yes.
I'm taking you a little bit back. Can you explain again in the diagram what we mean by breaking a system down to smaller system? Because like here it seems like they sum up to.
Okay,
bigger
let's talk
energy.
about this. Is really important. This is really important thing, and of course, in physics, you kind of see it very often, but not that people are really conscious about it. So I have a system, okay, and it has, let's say, energy 2E. That's what it has. Good. Now I say, look, what happened for some unknown reason, and that it was broken into two parts, and this has energy E plus delta, and this has energy E minus delta. Okay, what would be the entropy of a uniform system? It will be S of 2E. Now I want it to be larger or equal, that S of E plus delta plus S of E minus delta. If delta is small, what I can do with my right hand side is to write it as S2 prime delta squared over 2. Okay? Which, I mean, minus S of 2E plus this. So I want this to be negative. But this is precisely convexity. Okay? The negative sign of second derivative, which is precisely the statement that this is below this.
Okay. Also, this is S of E, not S of 2E. Like in a diagram.
Again, there is one way is to think about halves, but I prefer that I define my whole system with two energy, right? Okay. More questions?
So
Oh, okay. So just notation. Okay, like no.
It's just notation.
No,
yeah.
no. I mean on the diagram. On the diagram, you wrote E. On the diagram, it needs to be half E plus delta. Half
So
E.
what stands here is S of E plus delta plus S of E minus delta over half.
Okay.
Because you broke it into halves, so each one is halves.
So, did you say now that the graph of S as a function of E cannot be concave, must be convex?
Yes. As long as I treat my entropy as a positive quantity, couldn't be like this. Only like this. It's really important. Okay? And a little bit later, we'll kind of get some kind of freedom with that name. There will be some functions which are concave because they are negative or whatever. But generally, convexity in a mathematical sense means the constant sign of a second derivative. And in this particular case, as long as we treat energy and entropy as positive, it's convexity. Everything is below. Because our second law of thermodynamics is the maximum of entropy, right? We don't know. What convexity also important, guys? And this is something which helps, at least my intuition. At any point can be reached from inside by a straight line. It's really important. This is how there is no such thing, right? Because now from here you cannot reach this by a straight line, right? So it's something about kind of maximum, etc. Okay, good. Now, we already defined one quantity. This is a definition. For some reason, and you can immediately forget what I'm saying, it's called equations of state. Namely, the first derivative of extensive quantities with respect to extensive quantity are intensive quantity. Namely, what is extensive quantity? If I take one big system, it has E1, another has E2, I add them together and I assume that the energy is the sum. It's a very strong assumption. It means that the interaction in the system is short range and whatever is in the boundary between them is really unimportant. But what does mean extensive? Temperature is intensive. It does not change if you just, take two systems with the same temperature, add them, it will be the same temperature. By the same way, you also derive, for reason which I always hate, with the sign of minus, the derivative of energy with respect to another extensive quantity, which is volume. And you also define chemical potential is now with a plus with respect to the number of particles, or number of moles, or whatever, how you count matter in your system. This is with a minus for the reason that you assume that if system makes a work, it decreases its energy, right? So that's which essentially tells you that dE, which appeared in our first law of thermodynamics, which we already disappeared. You remember it was. What's important in this formula is that this is a differential, means that there is a function E. For every state, there is a value of E. Change of energy only determined by where you started and where you ended. These are not differentials. When I use delta means that the change of heat depends on the process. One way would give this Q, another way would give you that Q, and the same is W. Now with this three definition, we can write it in the form that you find familiar. And then you recognize that this is a visible part of energy change, namely work, and this is heat. So we start to understand that this entropy, which is related to something which signifies the maximum, is somehow related to the hidden degrees of freedom. It tells you that in the equilibrium, something about these hidden degrees of freedom must be at a maximum. And of course, on the lecture 3, we start identifying it with uncertainty. Our uncertainty about hidden degrees of freedom reaches maximum at equilibrium, which, from the language of information theory, means that you forget everything except the most basic integrals of motion of your system. That means equilibrium. Equilibrium is a state with maximal ignorance. So now we see a hint of it. Okay?
Can you define hidden and in which sense TDS is hidden?
Just literally. I mean, when this is a volume, it's a piston, right? It moves. You see it. You measure it in centimeters how much it moves. Okay? This you weight it, right? You know how much is mass there. This you don't. Okay? Yes.
In degrees of freedom, what do you mean by that? Like the temperature that you can't
Forget that I said it. It's a very poorly defined thing. It's wrong for me to use this. So for this moment, there is no degrees of freedom, which is a poorly defined thing. It's just a statement that something about our system we observe. For example, a volume, okay, of weight, and something we don't, namely a kinetic energy of molecules inside, which is heat. Okay, but the definition of degrees of freedom and to what extent there could be introduced independent degrees of freedom, let's not open this Pandora box. So just a statement that something we observe, some properties of a system we observe, changes of these properties we call work. It's a definition of work. Work is observable part of energy change. I really want you to see it, because the moment that you take it and start applying it to, I don't know, biology or data science, you really need to be in a very abstract way. What is observable is part of your conserved quantity. It's called work. Just by tradition. And what is unobservable is called heat. And we religiously believe that there are some gives us the change of energy which is conserved. Okay? Incidentally, energy conservation, namely that heat could come into work and work into heat, is Mayer and Joule, 1842 and 44, I guess. So it's 20 years after Carnot. Carnot didn't know. For him, heat was a conserved quantity. Right? Okay, good. So now,
Question?
yes.
So theoretically, if some new equation pops up, can it reduce some of the uncertainty that is compartmentalized in the heat
Absolutely.
section and move it to the observable ones?
And we'll be doing. You know, you probably already know, if not, the most discoveries are made by PhD students. The most important discoveries. And so, exactly 100 years ago, this one PhD student in the corridor of Berlin University met a relatively young professor and told him that he actually knows that what is about Maxwell-Demon. We will have the whole lecture about it. This is something, if you get some new knowledge about the system, it immediately means that you have less heat and more work. You can do more work. And that was Leo Szilard and Albert Einstein. The reason that Szilard actually met Einstein and talked to him, because his advisor was Mark von Laue of Szilard. He was a Hungarian Jew who just came to, he did chemical engineering and also physics. And he hated the problems that he was given to solve. So he really didn't want to work on it. But you don't come to your professor who is Nobel laureate and say, look, I mean, I don't like this problem. So he went to another professor who was young and not Nobel laureate yet. He just got next year. No, but maybe already got. I don't want to solve this problem with von Laue. I want to write my thesis about this thing, and that's how information theory was born, actually, in his thesis. Okay, but it's really about it. Any new knowledge, and we'll talk a lot about it. Okay, good. Let's go forward. So now what I want to do, I want to change variables. And that's where I can, oh my God, I erased this. Okay. Yeah, it's a pity.
Is that important?
Yeah, it's a phone number of the guy who was.
It's on Zoom.
Okay, I'll try. So what we work so far, we worked with extensive functions of extensive variables, which is not always convenient, right? And so sometimes you want to work using intensive quantity as your independent variable. For example, temperature. Okay. So now let's say I have a function y as a function of x. I don't know, some function. And but I really want to introduce p, which is dy dx. Well, it's because this is a function of x. This is also a function of x. Okay. And now I may say, let's take y as a function of x, which I express through p, and that would be some function of p. Because I want to use p, namely derivative, right, as an independent variable. is this function what I need? Namely, take x from this relation, expressed it through p. This is just an expression, right? Would it be a function which characterizes the same curve in this plane?
I mean, the x-axis, the horizontal axis will be different. So it's not the same curve.
Let me try to, you're saying something right, but in not very, so what we're saying is that what is p? P is the slope, right? So this is p, okay? If for every p I specify y, then this curve would correspond to the same relation between y and p, right? That you meant, right? Okay. So what it means that if I define this function y as a function of p, then all the curves shifted in this direction would give me the same. Because this is actually not a function. It's a differential equation which I need to integrate, and so it's integrated up to a constant which is shift with respect to x. Okay? But I don't want a function of p. So what it is, this function must be? Apparently not y, something else. What do you want to specify so that you really want to nail this curve and not that? This I don't want.
Will you interact with the y-axis?
Huh?
Your intersection with the one of the axes?
Your intersection with one of these. So what you're saying is that if I specified p, this straight line, what is really nails this and not this is where it intersects this axis or that axis, right? That's a great Frenchman by the name Legendre, and for some technical reason, it works both ways, you're right, but for some technical reason, Legendre did it on a vertical axis. So he said, let's for every p specify the point psi of p where x is equal to 0, where it intersects vertical axis. Another p, let's say this one, right? It would intersect it over here. Because Frenchmen are geometers, that's why I always envied about them. They treat, us, Legendre, you treat this curve as an envelope of straight lines, right? So every straight lines give you this point. As you change the slope, you create this curve as an envelope of your straight lines, and you define it by the function psi of p. Okay? So that y, which is this, and this is for a given pi, this is my y. It consists of psi of p, this position, plus p times x. This is p, my slope. This is x, my position. Okay? Or, because I'm interested in psi, I would say that psi of p is y minus px. Okay? Let me remind you that this is a derivative. By definition, pi is dy dx. So that's a construction, yes?
Why P is unique? Like if Y is concave or something. So you can have many P's and causing the...
You already answered your own question by the...
okay.
Because it's concave,
Okay.
then its second derivative is sign definite. Not necessarily positive or negative. Sign definite. Could be positive, could be negative. Then for every x there is only one P. Okay? And it's a very good remark. It tells us that here convexity or concavity appears in a totally different and new context, namely as a condition that your derivative has in a one-to-one correspondence with your x or with your y. Okay? Because if my function would be something like this, you cannot do Legendre transform, right? Because you would have here slope the same as here slope, right? what is important is, and this is the second time, and I promised you that convexity will be all over the place. This is the second time that you understand that the fact that you have a convex function, because in a moment, of course, we'll do it for this. Okay? So now, of course, if you do now take this formula and take, you've learned all this, right? It's not that it's the first time you see Legendre transform, right? I just want you to kind of have it because we'll be using it. But because if you did not, then just go and read a little bit more about it. It's a beautiful subject, and it's something which is a part of a very basic kind of intuition, right? Geometry is important. That's the way, just ask Greeks. So if you do deep psi, what you find is you get sorry. Yeah. So that I would get from here, I would get minus p dx minus x dp, and from here I would get plus dy, right? But this is exactly equal to this, which tells me the following thing, that d psi, no, x dp, p dx, right? So dy over dx is p. And am I too messy here? You want me to write it? Let me write it here. Psi of p, y minus xp, d psi is dy minus p dx minus x dp. Now, these are equal to each other. By definition, p is dy dx. Right? That means that d psi dp is minus x. It defines inverse Legendre transform. I can take psi of p, introduce a new variable, which is the derivative of psi with respect to p, call it x, and define a Legendre transform, which is y is psi plus xp. Okay? That kind of wraps it up, so it's like Fourier transform. You can go back, you can go forward. The only difference is a sign over here. Okay? Good. Is it clear? Okay. So now let us finish with this thermodynamics, because really what we needed all for is we needed for entropy, energy, and temperature. This was a sideshow with respect to y and x, but let's go back to so now if I have this function S of E and whatever x I have, how it actually solves the problem, for example, of what is the state of a system. And as we discussed this more or less several times, let's take a system which is separated into two parts that could exchange energy with each other, and its whole energy is fixed. So if there is changes, there could be more energy here, but then there will be less energy here. We ask, in what state we find this system if we let it wait long enough, and these two parts exchange energy many times. So what we have defined for each part of it, we have S entropy. So we have S1 of E1 and S2 of E2, and we have this extra condition. Okay? So now it's a very simple statement, is that if you look at the change of entropy, upon any energy exchange, let's say that my first system acquired energy dE1. Then the change of entropy is, of course, this one, right? Now, the change of entropy of a second system is dS2 over dE2, dE2. But dE2 is minus dE1 because the energy is conserved. So what follows from here, right? So I can write it minus, and I can write it 1. Which means that 1 over temperature 1 minus 1 over temperature 2 dE1. And of course, it's non-negative by second law of thermodynamics. So whatever happens, what it tells us that our pretty formal definition of temperature as a derivative of energy with respect to entropy works. If my temperatures are positive, right, then this is larger than this, means that T1 is smaller than T2. So if this is positive, this must be positive too. Indeed, if this has a lower temperature, its energy is increasing. And in equilibrium, it must be 0, which means T1 equal to T2. Okay? And that's how it works. You have this function, you differentiate dS1 over dE1, you obtain 1 over T1, and it's a function of Ex. So this statement is that T1 as a function of E1x is equal to some other function, generally E2 x2. And this equation, by solving it together with this condition, you obtain E1, E2. Could be complicated equation. But the statement is that the temperatures of these two systems must be equal to each other. That all makes sense in the... And now, what I want to do, the last thing is in this lecture, is to apply this thing and pass from this function of E to some function of temperature. Because now, if I would really, let's say, keep system at the same temperature, it would be nice to have temperature as an independent variable, right? So the question now is, what function something as a function of temperature I need to introduce starting from energy as a function of entropy. What is this? It needs to be done by Legendre transform. What is Legendre transform? It tells you, take your original function. So now your y is your energy, your x is your entropy, and your p is your temperature. Right? Is it clear? So what I should write here? Well, this function, I don't want to write it because then we would immediately know what it is. So what is the function which is a Legendre transform of E of S?
E minus ts.
Of course, because this is dE ds, that's my P, this Ts, okay? And of course, it's called, and as always, we ask the most basic question, why the hell it's called free energy? Never ever accept any term until trying to understand why people call it this name. It's usually a lot of things going beyond this. The people who do these things are usually geniuses. And they choose name after a long, long process of thinking. What is free? Free of something? Free for something? What is free about it? What's called free energy?
Available for work.
Huh?
Energy available for work.
Yes, it's available. It means it's the energy that we can free to use for work. And this energy was not free. Why now it's free? And then before it was energy. Energy is an ability to do work, right?
Free of uncertainty.
That's a Greek energy. Okay?
Free of uncertainty.
No.
It's observable.
Nothing free of uncertainty.
It's with observable variables.
I don't understand.
Because I can keep the temperature fixed.
Yes. It's a free to use for work, keeping the temperature. It means that it is now we're talking about the fact that our system that does work, it has energy E, is inside of some very large system, which is usually called reservoir, and it has temperature of this reservoir, and it keeps temperature over here. So what it tells you now is that we had energy before, system was with the energy, there was nothing else but the system, we can use this energy for work. Now we say, no, we live in this world, and in this world there is this temperature around us, and so we only kind of free, but is this free energy more or less? This is the fact that we are in a thermostat, having this temperature imposed from, means that we can do more energy or less. Intuitively, answer immediately. What's your feeling? More or less? Less. So we have this thermostat, reservoir. Reservoir is a good word, right? It's a reservoir. We can take something out of it. And yet it's less. And that's why it's called free. It's only you can use a part of it which is free to use. Of course, the work that you can do will be your energy plus energy of a reservoir. I'm sorry, I hope in a bit I'll be in a better form, but I just came from minus 20 degrees Celsius. That was cold. So now you can write this as a dE plus temperature of reservoir does not change, so it's just a change of the entropy of a reservoir. But because I assume that whatever changes of entropy here, it will be the same entropy here, namely I consider this type of quasi-static processes and all this, because I'm now trying to estimate what is the maximal work I can do. So I would write it as this. And of course this is exactly E minus Ts, because the temperature of my system is the temperature of a reservoir. We interpret and reinterpret and reinterpret this many times. Well, we'll be talking about self-driving car, for example, or information bottleneck, or any AI algorithm. Of course, there are always this type of functional appearance which consists of two parts, right? And so at some point you can say that if you have more entropy means, and I'm jumping now ahead, your uncertainty about the system is larger. The larger is your uncertainty of the system, the less work you can do. Economists say the larger is your uncertainty about your system, the less is purchasing power of your money. It's the same form, the same state, exactly. Okay? Now, it's something which is, the moment you start thinking not about isolated system, but in a system with a thermostat, so the temperature appears, it immediately subtracts from energy this Ts part. And now, what physicists are obsessed in the last, 70 years with phase transition. So you say, okay, my system now, because it's in a finite temperature, it goes not to the minimum of energy, like in this closed system, but to the minimum of free energy. But there's two ways to reach a minimum of free energy. You can decrease your energy, which usually requires ordering system. Right? For example, you have your spins interacting, right? You want to decrease your energy just by making them all looking in the same direction. Okay? But you can also decrease your free energy by increasing entropy, namely making system more disorderly. And that's what happens when you change temperature. You pass through phase transition. When your temperature is low, you have a crystal, namely that this part totally dominates. Crystal is a system in which you're so ordered that your energy is really very low and your entropy is very small. Now, when you increase temperature, the role of this guy increases more and more. And at some point, you melt your crystal because it's much more now, you can have much less F by having more S, right? So this formula, and of course, it now works when people do, let's say, neural network AI algorithms. They have this parameter, which they also call temperature. They are all former physicists, of course. This is a parameter which negotiates the balance between order and disorder. What is more important? And then they find out that as you tune this parameter, suddenly your algorithm just from working like a week to working like 2 hours. And they're very happy about it, and so they're looking for that transition. This is one of the maybe 5 most important formulas in technology, not in physics. Okay? That's why it's so important to understand what is free energy. And in the book you can find a cartoon about free energy. Kind of funny. Okay, good. The end of the lecture. Questions?
If you change free energy by changing the energy, then you assume that the conserved quantity of the energy is changing.
Yeah, because I'm not in a closed system, so my energy is changed. It's only a closed system that energy. Okay, so guys, so we don't have a tutorial tomorrow, so we'll meet in a week. I expect you to look in the book. Okay, take your own time, but at least I want you to have a feeling, and in particularly, you're welcome to start the next lecture from asking questions. Okay?
The first chapter plus.
Just read as much as you find interesting. At some point, reading is a very individual experience.
אין לך בכלל שיעור?
נראה לי שאין, כאילו בגלל...
כי בזה של המועדים, כאילו זה היה כתוב 9 עד 11. היא לא סגור, יכול להיות שיש הרצאות עד 11. יש לך משהו מחר? ירשום לאיזה 6 קורסים. תמיד יש לי משהו. עשית הקורס של Basic Concepts in Complex Systems. ממש אהבתי. כאילו, קצת תפסת מעוגל על הפסק כזה. זה הרבה נושאים כאילו. כן. אבל זה תלמה כזה מכל... לא מספיק. השאר אין הרצאה, נכון? אמרת.
אין למשל.
אין הרצאות בכלל? כי לפי
אני חושב שכן, אין בכלל. כדאי לבדוק באתר, אבל אני חושב שזה פשוט no classes. וגם בעוד שבוע. אוקיי.
תודה. אתה אומר כזה כאילו שזה, כאילו, טוב אני מניח שזה קצת כמו הקורס שהיה עכשיו של כאילו של סמינל פייפרס, לא?
יש לו 3 מרצים, אפי, אריאל ואורן.
שמדברים על נושאים שונים.
כן, כל אחד כזה, אפי מדבר על קונטיניום מקניקס,
על מה?
תורת הרצף, זה זרימה ואז כזה פלסטיות ודברים כאלה. ממש אחלה, הוא מרצה תותח.
הוא לא רשום ברשימה השנה, זה מעניין עם מודל.
יכול להיות שהחליפו אותו, אולי הלל, לא יודע. אורן עושה מערכות דינמיות. אורן, אתה גם מכיר, לא צריך להרחיב.
כן, אין שאני אוהב אותו.
אני גם אוהב אותו, אחלה, אבל אני לא ככה, כאילו, פחות התחברתי לחלק שלו אותו. כאילו זה מעניין, אבל לא יודע, קצת מוזר. ואריאל החלק שלו ממש אחלה, הוא תהליכים סטוכסטיים.
וכזה, מה דרום עם מטריקס תיאורי, נכון?
הוא לא נגע בזה,
הוא לא נגע בזה,
אבל יכול להיות שקיצרו את הסמסטר הזה, גם עכשיו כאילו הסמסטר לא ברוך מלא.
כן.